I figured out how to make WASD work on hexagonal grids for smooth, omnidirectional movement in a way that's discrete and deterministic for multiplayer. If I hide the grid, you would never even know that my character is moving one hexagon at a time. And you can add these controls to a game without any other part of your code knowing that these hexagons even exist. In this video, I'll show you how my character controller works, why I think it's great for top-down PvP games, share some of the theory behind it, and tell you about how I used an entity component system to help manage the code. If you're new here, welcome. This is episode 4 of my devlog series on creating a PvP sword-fighting action game incrementally, where every devlog comes with a playtest for you to try out in your browser, with no download required. I think you'll be surprised by how well it works. Our character has a position, a hitbox, and a set of 8 movement directions, W, A, S, and D, plus the 4 diagonal combinations from pressing 2 keys at the same time for 8-way movement. Hold left click and you can rotate, but then you might notice something strange. As you rotate, the direction indicators change based on whether our character is facing a point or side of the hexagon it's positioned at. This means that we have 2 different sets of movement directions for the 6 points and 6 sides, and the direction tiles are not placed at strict 45-degree increments, which is necessary if you want to map 8 directional movement to 6-sided grid tiles. I chose to make forward diagonal motion wide and backward diagonal motion narrow. I also made backward motion a little bit slower than going forward. When I first came up with this idea, I thought that I would need much smaller grid tiles for this to feel smooth, so I was pleasantly surprised by how well it works as is. But regardless, this design means that all movement can be defined as going from one tile to another, and therefore, all movement is discrete, which is a great property to have if you want to support deterministic multiplayer and features like replays. Hex-WASD is great for 2 reasons. It's modeled like a board game, but it doesn't feel like one for players. Let me explain. When you have movement that's tied to discrete grid tiles, the math and logic for your game systems becomes surprisingly easy. This is what the code for my movement system looks like, and you might be surprised by how small it is. When modeling movement like a board game, all you need to do in order to move the character is figure out which direction you want to go and add it to your current position. You figure out your target direction by combining your character's orientation with which of the 8 directions you've picked. This means that for multiplayer, you only need to send 2 numbers between players and your server to keep position in sync. You're also able to separate your game simulation from your rendering, which is how I was able to make my movement system feel quite natural. Even though the simulation is modeled on discrete hex grid tiles, the render layer uses animation smoothing so that the grid is invisible to players. You could even make the grid invisible to the other systems in your game if you don't want to model the whole thing with hexagons the way I am, because the hex grid is virtual and doesn't need to be rendered at all. It uses a little bit of math to convert regular Cartesian x and y coordinates into cube coordinates, applies some transformations in cube space, and converts them back to Cartesian for rendering. And you can make that conversion happen anywhere. All of this means that you get a very simple mental model, along with an efficient wire format for multiplayer. I learned about how hexagonal grids work at a conceptual level from this article from Red Blob Games. It's a fantastic resource, and it inspired me to apply the idea to the kind of game I want to make, a top-down with MOBA-like mechanics, which is what this devlog series is all about. So we have 8 directions and want to map them to 12 orientations of sides and points that we choose from the neighbors of our current position. Do we have to manually write out the 96 direction mappings? No, we only need to map out 2 sets, one for sides and another for points, so 16 directions. And once we have those, we rotate them by 60 degrees until we've made our way around the hexagon to generate the rest. Thanks to this mapping, movement becomes a matter of taking our current orientation and WASD input to get the grid direction that we add to the current position. Laid out like this, it sounds quite simple, but it took me longer than I'd like to admit to wrap my head around it and get things working the way I want. And what helped me manage that complexity is an entity component system. In episodes 2 and 3, I created a more typical movement system without any thought-out architecture, but the code was starting to get difficult to manage, and I felt that integrating the hex grid movement system would be a good time to clean things up. An ECS organizes your code into entities, which are just IDs representing the player for my demo, components, which hold data about entities, such as position or movement, and systems, which update the data stored in components. I was originally planning to use a library for my ECS, but my needs are quite simple, so I wrote a class instead. My ECS is a basic one with methods for creating entities, adding, retrieving, updating, and removing components, querying entities based on their components, and running systems on entities that have specific collections of components. There's also this notion of archetypes to key my entities by their set of component names to make querying a little bit more efficient. For anyone else using Three.js with React 3 Fiber, I want to note that I don't use React for any part of my ECS. I only use React for rendering, and there's a sync layer that populates my React state sitting between my renderer and game simulation. If you've watched my previous devlogs, you'll notice that my renderer's animation and movement code is much shorter and easier to understand. And the simulation's movement system is very short as well. This simplicity is enabled by my ECS, along with this module handling all of the cube coordinate operations. However, there is one React component that lives outside of the renderer. Its job is to collect player inputs from the raycaster and keyboard to pass on to the game simulation. And in the future, it will also send those inputs to my game server. Now, if you'd like to have the full source code for this playtest, and all my other ones, to really understand how features get implemented and changed over the lifetime of making a full game, the code is available for anyone that supports me on Patreon right now, or on YouTube once we reach 1,000 subscribers. You'll also get access to my Discord server for questions and discussion. I think this was the most important of the episodes focused on code, because I wasn't sure if everything was going to work out the way I imagined, but I'm glad it did. The focus for my next few episodes will be on creating some 3D assets for my game. I'm going to take the approach of blocking out my rough ideas to refine gradually, starting with figuring out the stylized proportions for my player model. Next episode, I'll create a very rough, low-poly mannequin in Blender and rig it so that it can run around in my scene. What did you think about my Hex-WASD movement controller? The whole thing is actually running with 12 frames of input delay to simulate a bit of latency. Did you notice? See you next time.